All right, let's dive into this really interesting research paper. It's all about a clever way to make one of machine learning's most popular tools, the Decision Tree Regressor, even more accurate. So first things first, we've got to understand the villain of our story. These hidden troublemakers that are lurking in pretty much every data set you'll ever come across. You know how it goes, right? It's that classic problem. You have this beautiful set of data, everything looks great, but then there are a few strange points that are just throwing everything off. Well, in machine learning, those are our bad apples. Now, the technical term for these things is outliers. You can think of them as the rebels, the points that just don't fit in with the crowd. They're rare and they stand out a lot. It's like this. Imagine your data is telling a consistent story, building a clear picture. Then one data point comes along and tells a completely different, totally bizarre story. It just doesn't belong and it can really mess things up. And this is why we really have to care about them. Outliers aren't just quirky little data points. They're actually dangerous. A lot of the time, they just come from simple measurement errors, but they have the power to completely mislead our analysis. And what's really crucial here is that they can absolutely cripple the performance of our machine learning models, causing them to make just terrible predictions. Okay, so let's meet the tool that's so vulnerable to these data saboteurs, the decision tree. A decision tree regressor, we'll just call it DTR for short, is one of the most widely used methods for making predictions. And for good reason. It's super popular because it's transparent, it's pretty simple to understand, and it's really versatile. So how does it actually work? Well, a DTR is kind of like a game of 20 questions. It starts at the top, at the root node, and it asks a simple yes or no question to split the data into two groups. It just keeps doing this over and over again at each interior node, making more splits until it gets to a final answer down at the bottom, at what we call the leaf nodes. The final prediction is just based on whatever data ended up in each leaf. But here's the catch. DTRs have a big weakness. Because they try so hard to account for every single data point, a wild outlier can trick the tree into creating these really strange, contorted branches just to make that one bad apple fit. This is a classic problem called overfitting, and it's where the model ends up learning the noise in the data instead of the actual pattern. And that overfitting, it leads to some really bad predictions. The model becomes this expert on its training data, including all the errors and noise. But then it completely fails when it sees new real-world data. So what on earth do we do about that? Well, this is where our hero enters the scene. To fix the decision tree, we need a specialist, an algorithm that's designed for one purpose and one purpose only, hunting down those outliers. Meet the isolation forest. It is a really clever and surprisingly efficient machine learning method that's built specifically to identify and isolate these troublesome data points. Its strategy is so simple, it's brilliant. Instead of trying to figure out what normal data looks like, it just focuses on how easy it is to separate or isolate a single data point from all the others. Think about it like this. It's way easier to build a fence around a lone house sitting by itself in a field than it is to build a fence around a house in the middle of a dense city, right? Well, outliers are that lone house. It takes very few cuts or splits in the data to get them all by themselves. And this method is just fantastic. It's fast, it works great even with huge, really complex data sets, and it gives every single data point a simple anomaly score, basically a number that tells us exactly how likely it is to be one of those pesky outliers. So now we have our workhorse predictor, the DTR, and our specialist outlier hunter, the isolation forest. The big question this research asks is, what happens if we team them up? And this, right here, is the core idea of the whole paper. It's incredibly elegant. Before you even let the decision tree see the data, you first send in the isolation forest to find and get rid of all the outliers. It's like you're giving the DTR a perfectly clean, pristine data set to work with. So the researchers built out this clear 5-step plan. First, you detect the outliers. Step 2, you remove them. Simple enough. Then you split that nice, clean data into training and testing sets. You train the model, and finally you see how well it did. It's a really logical and powerful workflow. And to prove this actually works, they didn't use some perfect synthetic lab data. No, they tested it on 2 messy, real-world data sets measuring air quality in India, the kind of data that's filled with the exact outliers that cause all these problems in the real world. Okay, This is the moment of truth. Did this whole pre-cleaning step actually make a difference? Let's take a look at the numbers. So the results were measured using something called the R-squared score. All you need to know is it shows how well the model's predictions match up with reality, and a perfect score is 1.0. Now, the standard decision tree was already doing really well, scoring a 0.9964. But by simply cleaning the data first, their new method pushed that score even closer to perfect, all the way up to 0.9976. In this graph, wow, this just brilliantly illustrates what that number actually means. Look at this. The yellow line is the real-world air quality data. The little red pluses, that's what the new cleaned-up model predicted. They are tracking each other almost perfectly. I mean, that is a visual representation of some seriously incredible accuracy. And if you're still not convinced, just look at the error rates. For these numbers, lower is always better, and the proposed method didn't just slightly reduce the error, it cut the mean absolute error nearly in half. That is a massive, massive improvement in performance. And the researchers' conclusion really says it all loud and clear. Teaming up the decision tree with the isolation forest outlier removal method demonstrably, without a doubt, increases prediction accuracy. The experiment was a huge success. So what's the big takeaway from all of this? Well, it really shows that sometimes the most amazing improvements in machine learning don't come from some brand new, impossibly complex algorithm. Sometimes it just comes from being smarter about the data we're using in the first place. And that leaves us with a really fascinating question. If something as simple as better data cleaning can get such powerful results here, what other big, complex problems are out there just waiting for a similar kind of breakthrough?